Hello learners, welcome back to the course on deformation processing of materials. In the previous lecture, we had started the metal forming process known as drawing. In that process, we saw how the drawing operation or forming process is carried out. Then we saw the parameters like drawability, the limiting drawing ratio. Then further we saw the anisotropies, which were normal and planar anisotropies. After that, we had seen the relation between the limiting drawing ratio and the planar anisotropy. And also we had seen some of the defects observed during drawing operation. Then we saw the Eitzen cupping test. After that, we saw some relation between some of the basic shapes which are drawn and the initial blank diameter or radius. And then we also had seen the effect of strain, that how it affects it, means how much strokes are required, that can be determined. Okay, so now let us begin today's discussion with some fundamental or basic numericals so that it will be easier to comprehend the concepts or relations. Okay, so our very first numerical for today will be a very simple question. Suppose we are given with the dimensions of a drawn cup and we are required to find the initial blank diameter. Okay, so for a cup with following dimensions, find the initial blank diameter. Initial blank diameter. Okay. And the cup which is given to us has a diameter of 250 meters, not meters, it will be very high, 250 mm, let us say, and height of 200 mm. Okay. So say the cup is like this. Okay. And its diameter is given as 250 mm and its height is 200 mm. Okay, now we need to find dB. So in the previous lecture, we had seen the relation between the diameters of blank and the diameter and height of this cup. Okay, so how, if you remember, how we got that? By equating the areas. Okay. So if dB is the initial initial blank diameter, then if we equate the areas, pi by 4 dB square will be nothing but the area of the curved section of this curve plus the area of bottom surface, which is circular cross section. So this will become pi by 4. Say the diameter of cup is DC, so pi by 4 DC square plus this was 2 pi RH or 2, if diameter is given, then it will be pi into DC into H. Okay. So this was the relation, and This pi gets cancelled out from everywhere. This 4 if goes that side, then it becomes dv will be nothing but under root of dc square plus 4 dch. Okay. And if we now substitute the values, we will get this dB as dc is 250, so 250 square plus 4 into dc is 250 and h here is 200. So this becomes nothing but this will be around 62500 plus this will be 1000 into 200. And if we solve this, I've already calculated it and it comes out to be approximately 512.35 mm. So this is the answer. So if we want to make a cup of this dimension, we need to go with the blank with diameter of around 512 mm. Okay. So now let us see one more example, numerical, based on the anisotropy. So if we are given with a specimen which has been subjected to deep drawing operation, then it shows around 30% elongation in length and 16% reduction in the width. So we need to find the normal anisotropy. Okay. So now the problem statement is a sample subjected to deep drawing shows 30% elongation in length and 16% reduction in width. So we need to find the normal anisotropy. Find the normal anisotropy. Okay. So if you remember, we had seen a relation for the normal anisotropy in terms of change in width and change in length. Okay. So simply, what was that? If you write, if you remember the relation, that was like R was nothing but ln of initial width by final width divided by, here the ratio was reversed. So this was final width by initial width and multiplied by final length by initial length. Okay. So this was the relation. Now we need to substitute the values so as to get the results. Okay. So since we are not given with the values of width and uh, length, but we are given with amount of reduction, so we can find that. Sorry. Okay, so 30% elongation. elongation means final length will be higher. Okay, so how we can write it? It will be final length minus initial length over initial length, and this is given to us as 30%. So in fractions it will be 0.30. Okay, so by rearranging we can write it as L over L naught is minus 1 is 0.30, or L over L naught is 0.30 plus 1, which will be nothing but 1.3, 1.30. Okay. So here we have the value of L over L naught. Similarly, we can find the ratio of width. Okay, so now change reduction in width is given to us. So reduction means the final width will be lower than the initial width. Okay, so this reduction is written as, also, since final width is lower, then W naught minus W over W naught is given to us as 16%. So this will be 0.16. Upon rearranging, here 1 minus W by W naught is 0.16, or simply W by W naught comes out to be 1.16. Okay. No, it should not be 1.16. It will be 1 minus 0.16, and which will finally become this will be 4 and 0.84. So 0.84. So now we have we have the values of these ratios. This is equation number 3. So from equation 1, 2, and 3, we can now find the planar anisotropy. Normal anisotropy. Okay. So R is nothing but ln of, this is W naught by W over ln of, this was W by W naught times L by L naught. Okay. So if we substitute the values here, what we get is, this is ln of, since we are having the ratio W by W naught, and we have to put here W naught by W, so it will be reciprocal of that. So this will become 1 over 0.84 divided by, this is ln of 0.84 multiplied by, this was 1.30. So upon solving this, if we do that, I have already calculated the values. So this comes out to be around 1.98. Okay. So this is the value of normal anisotropy if we are given with the amount of elongation or reduction in length and width respectively. Okay. So with this, we have completed this relation between the initial blank diameter and final product dimensions, and we have also seen an example of the anisotropy. Now let us see one more important aspect or thing related to the drawing operation. So there is a term known as forming limit criteria. Okay, so let us see what it is. So forming limit criteria is a tool or technique which is used for controlling the failures in sheet metal forming. Okay, so what happens here is uh, there is a diagram known as forming limit diagram, or it is also known as Keeler Goodwin or Goodwin Keeler diagram. These were two scientists who worked on this behavior and developed a diagram which is used as reference to predict the failure or safe operation or safe regions during the drawing operation. So let us see how it happens. So we will now see the forming limit criteria. Forming limit criteria. Okay. So basically what happens is to determine this, what is done is when the sheet metal is being formed, a grid of circles is made over the sheet using some electromagnetic or electrochemical techniques, and means etching techniques. And then when the sheet is deformed, these circles get strained. They deform and become in the or take the shape of ellipse. So there is a strain in the major direction or major axis, and there is a strain in the minor axis also. So that strain is measured and uh, referred to as the major strain and minor strain. And this is again plotted on or located or pointed on this reference diagram, which we will see. And in that manner, it is predicted that whether the component is going to fail or will it be safe. Okay, so let me draw the diagram first. So suppose, let me take the shape for better understanding. Okay. So simply let us see. This is like this. Here we plot the minor strain on x-axis, and on the y-axis we plot the major strain. Major strain. The positive side of the x-axis represents tension stresses, tensile stresses. Basically, we consider the tensile stresses to be positive as a convention. So this positive side represents tension region, and on the negative x-axis there are negative values also, so they represent the tension compression region. Tension compression because x-axis values will be negative, but we will be on the upper portion of y-axis only, so they are positive values, so they represent the tension values again. So tension compression region. Okay, so see, these are the values, like this is say 0, then we have values like 20, 40, 40, 16, 80, and so on. And on this side we have say -20, -40, -60, -50, and like that. minus 40, 60. Okay, so these are the values. Now, what Keeler did was he studied the tension behavior. Okay, and he predicted these values and put them. Let me draw the y-axis values first, then it will be better to understand. So say this is 20, 40, 60, 80, 100, 120, etc. So this is 20, 40, 60, 100, 120, and so on. So as I mentioned, what Keeler did was he studied the tension region and predicted this curve as like this. These diagrams are different for different materials. So let us say firstly, the one which I have drawn here is for steel. So it will be like this is the tension region, and similarly Goodwin drawn predicted the diagram for tension compression region. Okay, so this is much more steeper. So it goes something like from here to here. So this will be like it will be like this. So this is the Goodwin region. Okay, so let me label it also for better understanding. This is tension region. This was given by Keeler. And this one is the tension compression region. Tension compression region. This was given by Goodwin. That's why it is known as Goodwin-Keeler diagram. Okay. And also there is a tendency of balanced nature of stresses. So this is the balanced biaxial value. Here values will be somewhat balanced type. So say this is okay. So this is balanced biaxial. So what this diagram represents basically is these particular sections, these sections Above the lines represent failure. Okay. These represent failure. Let me change the ink color. So this is failure. Means any point which lies above these curves will indicate towards failure during the sheet metal forming process, and below this will be the safer region. And uh, how is it predicted? As I mentioned earlier, that by electromagnetic or electrochemical etching, circular grids are made onto the sheet, which are then measured initially, and after the deformation, the dimensions are measured again, and by that, the major and minor strains are determined, and the particular points are plotted onto this. Okay, so basically, this diagram, let me write first, is the forming limit diagram. Forming limit diagram, or the Goodwin killer diagram. This is FLD also, abbreviated as FLD, or the Goodwin killer diagram. Okay. This was balanced biaxial. I forgot to mention it. Balance biaxial. How these appear? Now let me draw that also. So suppose a circle was made like this onto the sheet, and after deformation, it becomes something like this. Okay. So here in this direction will be the minor strain, and this will be the major strain. Okay. So this was the initial shape, and this one is strained state, and here this is the this is say minor strain, and here it is used for measuring the major strain. This is how the deformation of grids measured. Okay, and as I mentioned, in case of balanced biaxial, the circle will simply either expand or collapse. Means it will be circular in shape, it will remain circular, not become elliptical. Okay, so in case of balanced biaxial, it will be something like, say, if this was initial condition, then the final will also be like circle only. Something like this. So here it is initial, this one is initial, and this is strain. This is for balance biaxial. Okay. and the techniques used for etching are electromagnetic and electrochemical etching. By that, these type of circular grids are made onto the samples. Okay, so electromagnetic etching and electrochemical etching are used to make the grids. Okay. So this is something known as the forming limit criteria, and this diagram here is forming limit diagram or the Goodwin killer diagram. In order, it is used in order to predict the failure in case of sheet metal forming. So this was another important concept. So with this, we will now uh, close the discussion for this deep drawing process. We have seen an broad overview of the entire deep drawing process or cup forming process. Okay. So now let us see the next metal forming process. So we will now start with the wire drawing or bar drawing process, which is also a metal forming process used for forming sections like rods, bars, and wires, etc. So let me change the ink color. So we will now see the wire drawing or bar drawing operation. Wire drawing, bar drawing process. Okay, so what does it mean? Basically, the process of reduction of diameter of some solid bar or rod by successively drawing it through various dies is known as the process of wire drawing or bar drawing or rod drawing, depending on the cross section and diameter of the formed product. Various terminologies have been used. Okay, so let me write it that the this is a forming process, or let me write it in other words that the process of reducing the diameters of a solid rod or bar by successively drawing it is known as wire drawing or rod drawing or bar drawing or wire drawing. wire drawing, depending on the final product. The means these nomenclatures are given based on the dimensions or diameters of the final product. Based on final product diameter. Okay. So this is also a forming process. Now let us see the schematic diagram for this process. So it will be easy to visualize it. We will also see what are the various components or regions called here. Yes, so by this process, basically, reduction in cross section area is done. Reduction in cross sectional area. Cross sectional area. Okay. So let us see the schematic representation now. So this will be something like. Also remember here the dies are sometimes called as bells. Bells or dies mean the same thing here. Okay, so say some um, so it will be something like this, this, then this. Again, a portion of relief is there, and similarly, here there is a reduction in section, not uniform. So firstly, it is like this, and this. So this is something like this. Then the bearing surface will come, and here will be the approach. This is the back edit. So this is the usual shape of dies which are used for the wire drawing operation. And it can be divided into 4 different zones, this entire setup. Also, there will be some casing which will be supporting these dies. So let me draw that also. There will be some steel casings. Something like this. And this can be, as I mentioned, divided into 4 different zones. Okay, so first will be the entry zone. Say here. This is the entry zone, first zone. Then comes the approach zone. What here? This is the approach zone. or second zone. It is bring it down to maintain the consistency. So these are the two zones. Then this one is the third zone. This is the third zone known as bearing zone. Bearing zone. And finally, last one is the exit zone. Exit zone or the fourth zone. They all have different functions to perform or different roles to play. Okay, so basically, this angle has an important role to play here. Firstly, let me write that this is the bearing surface. This is the bearing surface. Okay, and this angle here is alpha. This is known as the approach angle or half of the diangle, because diangle will be 2 alpha, alpha on the upper side and alpha on the lower side. Okay, so this is alpha, and similarly the angle this side is known as relief angle or clearance angle, beta. So this is beta. Um, as I mentioned earlier, this is the die or bell. What is happening? Die, uh, bell. Similarly, there is a die at the bottom side or lower side. Alpha is the approach angle, and this is the arrangement for wire drawing operation, the die setup. Okay, so let us see one by one what is the role of each of the zones or sections. So entry zone is basically uh, made to put the initial workpiece into the die, and here it comes into contact with the lubricants and draws them along with it. Okay, so the initial shape also, if you see near the approach angle, is slightly tapered. Okay, so while entering the initial wire, it is also a sort of wire or rod only. So it is getting reduced in the cross section. Okay, so it carries the lubricant along with it. After entering into the approach zone, the actual reduction begins. Okay, so before the bearing surface and after the entry, the actual reduction takes place. And when the reduction has taken place, it reaches to the bearing region or comes into contact with the bearing surface. The role of bearing surface is not to cause the reduction. It only basically provides the frictional drag or helps to achieve the proper surface finish of the final product, so that after leaving the die, it does not have damaged surfaces, or it also maintains the uniformity of the cross section of formed product. It does not cause the reduction basically. Okay, and after that there is a relief angle or clearance angle, that is this tapered section of the die towards the exit zone is known as the back relief also. So it basically allows slight expansion of the metal, so that when it leaves, there is no aberration, or means when there is a stoppage in the drawing process, there is no damage into the drawn wire. Okay, so this provides a buffer type of region to uh, make the proper exit of formed wire. Okay, so let me write these things also. So basically, the shape of or the entry zone allows the lubricant to enter along with the wire, along with the wire. Okay. After this, the approach zone leads to reduction in the area of cross section. Approach zone leads to reduction in area of cross section. The area of cross section. Okay, and generally, here comes the approach angle or the die angle. And die angle, in general, we when we see die angle, we consider alpha, but actually die angle should be 2 alpha. So from now onwards, we will, for our convention, use die angle as alpha only. Okay, means we will consider the approach angle and die angle to be alpha. So whenever we see or say write alpha or die angle, it will mean the approach angle only for our convention. Okay, so here basically the die angle alpha lies in the range of 6 to 10 degrees. This is the range of this approach angle. And after the wire passes this approach zone, the turn comes for bearing surface. Okay, so the bearing surface refinishes. Its function is to refinish or to provide the uniformity to the form product. Refinishes the form product. Okay, so it does not lead to any reduction. Does not cause reduction. After the bearing zone comes the exit zone, where the drawn wire leaves the die or bell. Exit zone, exit zone, or back relief. Basically, allows slight expansion, as I mentioned earlier. Back relief allow slight expansion and allow the exit of this drawn wire. And allow the form wire to leave the die. Okay, so this is the rule of all these four zones: entry, approach, bearing, and exit zone. Also here, we have mentioned about the clearance angle. So the clearance angle lies in the range of around 25 to 30 degrees. So clearance angle beta, this lies in the range of 25 degrees to 30 degrees. Okay, so this is the fundamental representation of wire drawing process, or the schematic setup of the machinery or dies or bells which cause the wire or which lead to wire drawing, which contribute or which are used for wire drawing. Okay. So again, there is an important point that in the wire drawing process, tensile stresses also act along with the compressive and shear stresses which are used in metal forming process. Here, tensile stresses are also used. This we had seen in the very beginning also when we were classifying the forming processes, that the wire drawing operation falls into the category of uh, tensile stress type of forming operations. Okay, so in wire drawing, tensile stresses also act along with compressive and shear stresses. Compressive and shear stresses. Okay, so now let us see how various parameters vary and what are the steps followed for this operation or this process of wire drawing. So what happens here is, if we want to see the reduction, basically what happens during the wire drawing process, say initially we had a rod or wire of some initial thickness, sorry, diameter, then For our discussions, we will now consider the cross section to be circular, so it will become easier to understand and visualize. The cross section may be square shape also, so it will be bar drawing. Okay, so we will consider circular section for now, and this will be rod or wire drawing. Okay, so this is say further reduced to some radius r1, which is then again subjected to drawing, and this again reduces to form r2. This is again subjected to some forming operation, and this becomes r3, and if further formed, it will be formed as a wire or rod. Okay. So say like this. Okay. And here it is pulled using tensile load, or is generally coiled in a uh, coiling system. So here R1 will be higher than R2, which will be higher than R3, and this follows. Okay. So keeping all this in view, the percentage reduction will be given us. We have seen the fractional reduction also. So if we multiply that by 100, we will get the percentage reduction. So percentage reduction will be here the cross-sectional area is decreasing. So initial area minus final area over initial area multiplied by 100. This will give the percentage reduction. Since we are considering circular section, so in terms of diameter also we can write this. So it will become initial diameter square minus final diameter square over initial diameter square into 100. Okay, this we have derived frequently, that pi by 4 d naught square minus pi by 4 df square by pi by 4 d naught square. So pi by 4 gets cancelled out from the numerator and denominator. Okay, so this is the percentage reduction. Now, some basic requirements for the initial stock or billet are there, that it should be in annealed condition, because there will be a lot of deformation. It will be suffering during the entire wire drawing process. So it should not have initially it should not have any residual stresses or anything like that. So it should be in annealed condition. So the initial stock or billet should be annealed. Initial stock or billet should be in annealed condition. Okay. So these were some requirements, and basically type of reduction or means type of variations occurring during the drawing process. Now let us see some of the major steps for drawing operation which are followed. Okay, so let us see the steps for drawing. Uh, Here we are again saying drawing frequently, only drawing word I am using, but here we are referring to wire drawing. This is different from deep drawing, keep in mind. So deep drawing was a sheet metal forming process. This is a sort of bulk metal forming again. Steps for wire drawing. Wire drawing operations. So the very first step here should be, as I mentioned, the stock should be in annealed condition. So first step will be to do the annealing. Annealing of stock. Okay. After annealing, since the stock will be in contact with several dyes, so uh, we should keep in mind that it should not damage the dyes, and also it should not have any kind of defects onto the surface, so it needs to be cleaned. So the second step will be cleaning. Okay. And when we are completed with annealing and cleaning, we now can go for the drawing operation. Okay, so let me write the type of cleanings that we can use here before we mention about the drawing. Okay, so cleaning can be by acid pickling. So acid will dissolve any kind of grease or uh, means any kind of impurities which are present on the surface. Okay, so firstly by acid pickling, here degreasing can be done. It will dissolve the greases or other as foreign materials are present in any. Then tinning or coppering can be done. So here some coating is done, some tin, copper, or any other ferrous coating is done by electrolysis process. So during the wire drawing process, it will act as a lubricant film. Okay, so tinning or coppering. Okay, so here what is done is coating, coating of tin, copper, which will act as lubricant. So this is done during the cleaning operation. And after the cleaning process, we can go for the drawing process. Okay. So after this, we go for drawing. Also, apart from drawing, a process known as swaging can be done. Swaging is then followed by wire drawing. Wire drawing, we have seen how it is carried using the dies. The stock is pulled and coiled, and during this, it passes through the die where it gets reduced into the cross section. Okay, so let us see what is swaging. Swaging, I will tell in a while. Swaging can be done then drawing. Okay. So what is swaging? Swaging basically means uh, die hammering type of process. Here, there is a die which frequently hits the stock or wire, and it gets reduced into the section, and then it is simply drawn further. Okay, so in swaging, a die hits the bar or stock, and therefore diameter is reduced. that is reduced. Okay. This is also known as die hammering or kneading process. Also known as die hammering or kneading. Kneading, we do for wheat flour. Similar kind of process is being done here also. Okay, so let us stop on now, and in the next class we will continue our discussion on this wire drawing process. So thank you everyone.